Hi, welcome back. I'm Professor Ronald Vincent M. Santiago, and today we'll be discussing Module 12, Problems on Case 1, Unloaded Generators Considering the Single Line to Ground Fault. Now, this is an example of a single line to ground fault wherein there is a fault at point F. In the diagram, we have one generator and two transformers and a transmission line. So the fault point is located at the end of the transmission line connected to transformer T2 on the Y-grounded side of the transformer T2. So a single line to ground fault occurs at point F. Assuming zero fault impedance, find the phase currents in the line, assuming that the voltage at the generator is equal to 1.0 per unit. So these are the given data for generator. The positive reactances equal to 40%. The negative reactance is 40%. The zero sequence reactance is 20%. For transformer T1 and T2, the reactances are equal to 5%. For the transmission line, the reactances, positive and negative sequence, 15%. The zero sequence reactance is 35%. So note, all reactances are in per unit of a common MVA base. So meaning all the reactances are adjusted already based on a common MVA base. Now, considering the location of the faulted point, we can now redraw the positive sequence network following this one-line diagram. So this represents now the positive sequence network. So we just place there the positive sequence reactances, likewise the generator, and indicate the location of the faulted point. In this case, we call it as F1. Now, this positive sequence network can be represented by an equivalent Thevenin circuit. You have the terminal F1 and the neutral reference N1. You have the generator value 1 per unit. J.6 is the sum of all the impedances in that positive sequence network. And you have the BA1 measured between the neutral point and the faulted point F1. So note that in that positive sequence network, IA to the transmission line is not equal to the generator current IA flowing to that generator, but it will be equal to the current flowing to the faulted point F1. For the negative sequence network, so similar connection or pattern to the positive sequence network, but without the sources. So we just indicate that the negative sequence reactances of all components in the system and determine its Thevenin equivalent. Now notice that the current flowing through the transmission line I2L in that negative sequence is equal to the current flowing through the faulted point IA2, but it is not equal to the current flowing through the generator. So it is not equal to I2G. For the zero sequence network, this is how it is drawn. We need to consider how the transformer is connected to the system. And in this case, it is connected in delta Y grounded. So we need to get now the Thevenin equivalent of this zero sequence network. So notice that the current flowing through the transmission line IOL for the zero sequence network is not equal to the current flowing through the faulted point F0. And IA0G is equal to 0 since it is hanging. Now, how it is interconnected, these three sequence networks for this single line to ground fault. Now, notice that the currents flowing are equal, IA1, IA2, IA0 are equal based on our computation. The interconnection of these three sequence networks will be in series. So, we now have IA0 equal to IA1 equal to IA2 equal to 1.0 divided by the sum of these sequence reactances. 0.6 plus 0.6 plus 0.044, and that gives us a magnitude of negative J 0.804 per unit. So these are the sequence fault currents flowing to the faulted point. Now, converting this into phase current, the phase fault currents will now be equal to, for IA, equal to 3 times IA0, equal to negative J 2.411 per unit. Whereas for IB and IC, this will be 0. Now, for sequence currents in the transmission line, IA1L is equal to IA1 equal to negative J 0.804 per unit. IA2L equal to IA2 equal to negative J 0.804 per unit. But for IAOL, that is equal to IA0 multiplied by the quantity J, 0.05 over 0.05 plus 0.4. So that is using a current divider principle, equal to negative J 0.089 per unit. So having these sequence currents in the transmission line, we can now solve for the phase currents in the transmission line. IAL is equal to IA0L plus IA1L plus IA2L, and that gives us negative J 1.696 per unit. For the current IBL, that will be equal to IAOL plus A square, IA1L plus A, IA2L. That gives us J 0.714 per unit. ICL, that is equal to IAOL plus A, IA1L plus A square, IA2L, and that gives us J 0.714 per unit. So that ends our module 12. See you in the next module.